So today, I want to go back and kind of look at a couple little things leading into hardware 6. So one is maybe to kind of help look at some patterns to kind of give you some suggestions. And so we'll kind of start there. So if you are looking at doing hardware 6, right? Whether it's the FSM or the decoder, right? We essentially said that most of the code that we have to do is going into either this execute state, or if we look at which colors, if we look at the decoder, right? We have this, right? This always comb block. Right, we did this thing where we set all of our outputs to zeros. And then we did this case statement with our opcode, right? Where essentially the opcode, right, is our 7 bits for the instruction. Or the lower 7 bits of our machine code instruction. Right? And so we set up all of these things for these options. And so, you know, if you start looking at, well, what does that look like? What are those options? And you see that there's essentially not a ton, but there's a few, right? So we have something like, we've got one set of opcodes for all of the R-type instructions, right? And these are called, why are these called R-type? Anyone have an idea of why these are called R-type?
Does it have to do with the fact that they only operate on registers?
Yeah, they only operate on registers, right? This has 2 source registers that do something into a destination register, right? And so, you know, add, and, or, shift, set less than, shift right, exclusive or, sub right. So if you look at this architecture, maybe, pull it up. Okay. This architecture for, let's say, add x5, x6, x7. So if we're looking at the decoder, right, all of our muxes. So PC source for this instruction would be what?
0.
RFWR select would be
3.
ALU source A would be
0.
ALU source B,
0.
ALU function,
All zeros.
zeros. Well, what if this becomes sub? What changes?
ALU function.
ALU function. Anything else?
I don't think so. I mean, everything, the ALU, the only difference is the ALU.
Yeah, something that changed. Okay, well, what about set less than?
Maybe 1. Oh, 2. Sorry.
Yeah, this changes. And so if we go back and look at our list again, add, and, or, shift left logically, set less than, shift right, arithmetic or logically, sub, exclusive or, right? The only thing that changes between those is what?
ALU function.
How you function. Okay. So if I had some option here, right? So let's just say, right, this is, right, this is essentially my R type, right? My ALU, or let's start at the beginning, right? PC source, right, is set. ALU source A, ALU source B, RF, WR, select, right? These are all set. And this is essentially the same for all of the R types. And so the only thing that's different is this ALU function. It's the only thing that's unique. So how could I handle setting the ALU function?
With a case statement on the 3-bit opcode.
Okay. Yes, that seems like that would be an option, right? I use the 3-bit opcode to set all of them. Let's look at this.
I have a question.
Yes.
So can you put a case statement inside of another one? Is that how this is going to work?
You can.
Okay.
In fact, we did this. We did this in the FSM, right? We had a case for state, and then we had this case for opcode inside the execute case. Muxes leading to muxes, leading to muxes. It's like mux inception. Okay. But I could see where you might be rushed into, let's just hard code all of these instructions inside a case statement. But I want to pause for a second and let's think about what we're doing here. So let's look at some examples. Add and let's see, what else could we do? Let's do a sub, shift left, shift right, arithmetic. Right? And so let's look at what the ALU function is that we want. Right? So this I can pull off of my architecture diagram. Right? So for add, right, my ALU function should be 4 zeros. For and, it should be what?
0 1 1 1.
Okay, sub.
1 0 0 0.
Shift logical left.
0 0 0 1.
Shift right logically.
0 1 0 1.
Shift left. Or shift right arithmetic.
1 1 0 1.
Okay. So now that we have that, let's look at what this function 3 looks like for all of these. And so that we can pull from our, maybe I can. It's going to be hard to get this all to line up. So add, the 3 function code is
Zero, zero, zero.
for and
1
One,
1
one,
1.
one.
sub
0, 0, 0.
Let's see, shift logical left.
Zero, zero, one.
Okay. Yeah, I can put this sort of here. Shift right logically,
101,
0, 1.
shift right arithmetic.
101,
And so when we look at this, a couple things might stand out. What?
the 3 bits of the func3 match the bottom 3 of the ALU func.
Yeah, look at that. Yes, that is one thing, which seems like probably not coincidental. What's the other thing? That's the good thing, but then we maybe notice a problem too.
The and
Some
and
of the
sub have
function
the
three
same
numbers are the
function
same.
3.
Yeah. Add and subtract have the same function 3, but do very different things. Shift right logically, shift right arithmetic, same function 3. So if I did a case statement off of function 3, yuck, that wouldn't entirely work. I mean, it'd get me most of the way there, but I'd have other things. So go back
So
to.
do you look at bit 30?
Yes. So if we look at, let's say, let's do shift right arithmetic versus shift right logically. How could I tell the difference between those two in their machine code?
There's the left 7 bits. The
Yes.
bit and bit 30 in particular is 1 or 0.
Yeah, 1 and 0. In sub, it's 1. And in add, it's 0. So it's this bit 30 that becomes useful, which, should sort of make sense that, hey, there's this bit 30 that we're sending into the decoder that you might have been wondering, why are we sending it in? Well, now that sort of fits. And so if I look at my bit 30, let's just do this. For add, bit 30 was a 0, a 0, a 1, a 0, a 0, a 1. And so what could I do here?
Concatenate.
I can concatenate these two. And so this means I can use these to set this. No separate case statement needed. And so by taking 10 minutes to look, you probably just saved yourselves 20 some minutes of coding, a bunch of lines of code for sure. Okay. And then if we look at the next set, so the next set of instructions, we could look at the I type, right? And so we got a couple things that are grouped into this I type. We have our I types that would be, our add I, and I, shift left immediate, shift right immediate, or I, right? You have all of those. You have JLR, but notice it's a different opcode. And so that's different. And then you have your load instructions, which are also a different opcode, right? So these are called, why do we have all of these looped into what we call I-type? Even though they have different opcodes. Why is load and JALR considered an I-type instruction?
Because they have an immediate value.
Right, they have, and what type of immediate?
And I-type immediate.
An I-type immediate, yes. Okay. So if we ignore them, right, I'm going to ignore them for the moment, and we go to just the I-types, the other I-types, which all have a common opcode here. Right? So we could put that next in our case statement, right? We go down and say, let's do I-type. So notice we have very similar things, but we run into a problem. What's our problem with the I-types?
Multiple opcodes.
Okay, right. So if let's say I ignore the loads and the JLRs, right? So I just do add, and, XOR, shift. Those all have the same opcode. In fact, I guess we could go back here. Let's take a moment and so let's say I had add I, right? Right, something like this. What changes from the R-type to I-type?
Just source B, which
Source B
which should be
becomes
1.
And then we still have this same sort of thing where the ALU function, right, changes. But that's where we run into a problem. Can we do the same thing we did with the R-type?
No,
Why not?
because the bit 30 is part of the immediate.
Because the bit 30 is part of the immediate. Ick.
Can we assume it's 0?
Okay. So let's look at that. It's 0 for every option but what?
Oh, subtraction and shift right and elevate copy.
Yeah. Now, is the LUI going to be something we have to worry about for an I-type?
No.
No, right? LUI is a U-type, right? It's got its own opcode. So we don't have to worry about that one. That's nice. So we have a shift right and we have a sub that we have to deal with. Otherwise, we can assume it's 0. Okay. Seems good. So how do we handle the shift right?
There's bit 30 is available.
Hey, bit 30 is available. Why is bit 30 available?
Because you can only shift by 32 bits.
Yes, right. So remember, in your ALU, you should have only been looking at 5 bits of the immediate to shift with, not all 12. Because these are the only 5 that you shift. These are set. And you'll notice, right, for bit 30, so how do I know whether to use this or not? How do I know whether to use bit 30 or not to use bit 30?
Depending on the function, the value of function 3.
Yeah, so in this case, I know for my shifts, I need to use bit 30 in which case?
If you have 101,
If you have 101. What else do you notice about the I types here?
Subtract is not an I type.
Subtract is not an I type. Subtract was the other one we said we needed to have a 1 with. Don't have to worry about it because there is no sub-I instruction. Probably not a coincidence that there's no sub-I instruction. So, yes, the I types now become very easy. Maybe not all the I types, but most, right? You probably added, I don't know, another 7 or 8 machine code instructions, right? With a relatively simple setup, right? In the same sort of fashion that we did here. And so you could continue this, right? S type, U type, right? And you'll start to see patterns to how things were laid out and organized, right? That you go, this wasn't just random. You start to see where these numbers come from, right? These weren't just haphazardly selected in our ALU, right? These were very specifically selected for a reason. And you'll start to see that, right? And so I would suggest before you just start dumping, line after line after line in your system Verilog to lay out your decoder or your FSM, right? You think about how you could organize it and see if you can find some patterns, because some patterns probably exist because there's probably some method to the madness on how this thing got organized to make that easier. Right? Okay. Questions on that?
Yeah, I have a question. So when you said that we were supposed to concatenate the 30th bit 30 and then the function 3, can you write a concatenation inside the parentheses for the case in order to do that?
Just like you would assign this to something, you could assign this a concatenation.
Okay. Well, okay, what I mean is, like, when you write word case and then what's in the parentheses, isn't that where the concatenation format would...
So I need to concatenate these two inputs and assign it to this output.
Oh, okay.
Right, because I'm trying to control this output, this 4-bit output, and I can use this 3-bit input and this 1-bit input to control that 4-bit output when this 7-bit is something specific.
Okay, so you don't even so you don't even need another set of case statements because it just happens to be the same thing as ALU function.
Right.
Okay.
So when I'm in an R type, my ALU function follows a very specific pattern that I can just assign the output to be. And then I don't care if it's an add or an and or a shift, right? Because the ALU function will always follow this set pattern to be what the value is.
Okay.
Other questions? So this is sort of how you should go through, right? When you kind of approach each of these, right? I would see again, I'd set up all your different opcodes, and there's not that many, 7, 8, something like that. It's the only sort of, I think we only got about 7 or 8 different ones. And then each one of those, some of them are very specific, like there's a very specific opcode for LUI. There's a very specific opcode for JAL, for JALR. So those sort of follow. But then there's, all the store instructions follow a certain opcode. All the load instructions follow a certain opcode. All the, and I or I, right, that we looked at, of the R types follow. And so sometimes you can find a pattern so that, you don't have to come up with a case inside a case and list every single machine code individually. I mean, you can go that route and you can list every single machine code individually. But there's better ways, right? Cool. Questions? So once you have that, the next thing you need to do in hardware 6 is, right, you put some code, right, that it's given, and you want your hardware to essentially run this code. All right, so you throw this code into RARs, you go to assemble it, right? Gives you this nice assembly code listing, which is useful. We'll come back to this. But you can get this out into a mem file, right? Make sure you select hexadecimal text. It's the text section, right? You can dump it to a file, which will essentially give you a listing that you could then put in your, you could put into your mem file, right? So your idle.mem. And so here's my, essentially my 6 instructions. So I have made my CPU, which is really just a way to wire up all of these devices. Right? And so notice, right, they all show up. Nice blue dots, no weird red question marks anywhere. So everything probably looks connected. Other things you'll notice these are all named fairly nicely. I don't have things like hardware 2 or hardware 4, right? Because what is that? Who knows? I have things labeled. I've also organized these acronyms for them. And you'll see, right, like, mem. Notice like all the signals started with mem. And so I gave the instance the name mem, right? So that it matches. And so I did the same thing for all of these, right? So if I look at the signals inside my reg file, right, they all begin with this RF, right? And so everything all the way through. So it's nice, it's consistent, it's easy to identify, which essentially is going to make my lives easier. Okay, so then I make a test bench for this. And so notice in my test bench, right, I have a UUT for my CPU that shows up, right? Teal dots are good, red is bad. Everything shows up. So one thing worthwhile doing before you run a sim, I would do a synthesis because that does good air checking. And my synthesis gives me no warnings. Right? So you can synthesize the full CPU with 0 warnings, which is nice. So if you get warnings, there's probably something you could do to get rid of it. Okay, if I look at my schematic, stuff. I'll look at my schematic. So I should get something, right, that looks sort of like my piece of paper, just all the boxes are in different places. A couple things. One, you'll notice this interrupt signal is disconnected. And that probably makes sense because it's not used. Right? So in my architecture, right, this interrupt signal, even though I have it going into an FSM, right, the FSM never uses it. And so the hardware pulls it all out. So unconnected is typically something I'd be concerned about, but I see what's unconnected and go, yeah, I don't use it. So it probably should be unconnected. That kind of makes sense. Everything else appears to be connected properly. I've got all of my muxes here. If we look at what shows up in my FSM, my decoder is basically a bunch of muxes and some ROMs, which should probably sort of make sense. Right? If it's a case statement or a couple case statements with predefined set values, a ROM is basically a lookup table of set values, and a case statement is essentially a mux. Seems like that fits. The FSM portion gets a little messier. But again, some ROM, some case statements, and then of course, a present state register, right, which should fit. You should definitely have one of these in there. And then some ROMs and some muxes, which sort of fits. Okay. Everything else is kind of matching what you should have otherwise, right? So you get all of these parts that should look kind of what you would expect, but they're all there. So that looks fine. Close that. So now, elaborated design looks good, synthesized, no warnings. No, I don't want to do that. I can run my sim. And so you could run your sim sooner, but their simulation gives you bad error codes, right? So, I mean, they're all there in this TCL console, but you know, you got to go back and kind of look at what you're looking for. Whereas, you know, synthesis, even your elaborate design puts them right here in your messages tabs, gives you links directly to where they're at, right? So it's kind of nice. So my sim does this. One thing that maybe stands out is red's probably typically bad. In this case, I'm okay with it. First, if we look at, this is IO bus out. So why am I okay with it? IO bus out is essentially connected to my register 2. And so one thing I did maybe differently than you is in my reg file, I didn't initialize it. Okay. So I made sure that X0 was always going to be 0. And so I didn't initialize any registers. So until they get used, they're going to be X's, which I'm okay with because I shouldn't be using the register until I put something in it anyway, right? Because that's how hardware works. So anyways, that's why I've got X's, which you would think would be bad, but I'm okay with them. So I've got this code. How do I know, did my machine execute this code properly or not?
Do you want to add more signals to the sim?
Yeah, can you tell?
No, because we're not using any of the IO, so we need
Yeah.
internal signals.
Yeah, I mean, I wrote it, so I'm sure it's all good, but right, you don't know. And so this isn't really useful. What I have isn't really useful because, right, we go back and look at the instructions. Everything's happening internally. I'm not reading from any input, right? There's no external input. There's no load from switches. There's no load from any of my memory mapped addresses. And I'm not writing to any of my memory mapped outputs, right? I'm not writing to LEDs. I'm not writing to my 7 segments, right? There's no writing to any memory address at all, really. And so looking at these, right, I maybe could try to infer RS2 off of some of these instructions, right? Knowing that IO bus out is RS2 and IO bus address is my ALU result, you know, maybe I could try to sort that out, but really not intuitive. So I need to add some stuff. So what should I add? What would be good to look at to see if this code is working?
Probably the registers that you're saving things to.
Yeah, so my registers. So again, in my sim, right, scope, objects, right, I can select on all of these parts and I can see all of the internal signals, right? So a couple things, right, like reg file, notice all the RFs, right? Branch condition generator, branch address generator, immediate generator, right? Has nothing to do with the gram, right? So reg file. So I could look at all of these things like address 1. Right? I could drag those in. Notice they don't show up immediately. And so if I want to have this thing to show up, right, I have to tell it to restart. And then I can pick a certain amount of time and tell it to run for that amount of time, right? And so I can kind of see what's happening. So when do I want to look at the registers? When am I dealing with X5 or X12 or X13?
You probably want the instruction on there too, so you can tell where you're at.
I could look at instruction, but there's probably something else that I could use that I probably would use.
Program counter.
Yeah, the program counter would be really, really useful because otherwise this is just a mess of signals and there's no way to tie it to my code. But my program counter is my link, right? It's my common reference. So I know if my program count is something here, I know I'm dealing with that specific instruction, right? So it's my way to link my waveform and my code listing. So your program count you always want to have in there. And so there's a couple places I can pull my program counts, right? And that should make sense too, right? Because I could look at my program count in my program counter, or I could look at this signal. And so this signal in my CPU, I called all of those signals that are connecting things buses, right? So they're all something bus. So like PC bus, right? This would be my program count. But you'll notice they're all buses. And then except for control signals don't have bus. Okay. If I wanted to make sure this matched, right, I could pull it out from my program counter too, right? These signals should match all the time. If they don't match, I wired something wrong. Okay, so these match everywhere, which look good. So I'm going to get rid of this one. Okay. So other things, right? Signals start to get lost. And so I can do things like create a divider. To help organize this. Other things I can do, move stuff. I can take all of these signals and I can create them into a group. And so the nice thing about a group is that I can make them collapse or not. And so when I want to look at them, there they are. If I don't want them to confuse me from other stuff I'm looking at, I can make them disappear. And so this becomes very kind of handy. Now, I'm looking at my program counter. Notice my program counter exists for 2 clock cycles. Where do I want to check my reg file at?
In the second clock cycle,
Why?
because that's the execute state.
Should be, right? I probably could also bring in what? Here's the other signal that I always recommend bringing in. Bring in your present state, right? Because this will make your life easier. And so you can see stuff like this is when I want to look, when I'm in the execute state, right? I'm executing instruction 0. I'm executing instruction 4. I'm executing instruction 8, right? You don't want to sit there and have to think about which clock cycle you're on. Okay? So the program counter and your present state, right? Those are your references for this waveform, right? These are the references that you can sort of match what you would expect in a timing diagram, right? And so those become essentially necessary in essentially every sim that you will do once you've got your CPU running, because they're kind of our point of reference on what signals should be when. Right? You don't want to do mental gymnastics. Is the fetch the beginning or is the fetch the end? Right? Don't try to confuse yourself. Also notice that these are these names, right? And this matches what I said about using the enum, right? We use the enum for our state type rather than a binary number. And so see how easy this is to see, right? I don't have to think about was fetch 0 or was fetch 1 or was fetch 2, right? Like I don't have to think about it. It's right there in my face and obvious, which we like. Okay, so I could look at this. The other thing that's kind of useful, right? I could take my entire reg file, right? And if I want, I could bring every single reg and I could look at all 31 all the time. That's probably a bit overkill. Because in this case, right, I basically need 5, 8, 10, 12, and 13. So 5, 8, 10, 10, 12, and 13. I can drag them in. Have to restart, right? And so, first instruction, right? Happening when the execution of program counter of 0. Right? So this should do what? What will this instruction do?
Load AA055 into the upper 20 bits of X5.
Yeah. So X5 should become AA055 and then 3 zeros in hex. Right? When does that happen?
At the end of the execute state?
Yeah. Notice it doesn't actually change until the next fetch state. Is this good? Is this wrong?
I think that's good because it has to wait for the rising edge of the clock.
Yes. Remember in our timing diagram, right? This instruction for LUI is going to put, right, AA055000 goes in through my ALU, comes out, goes into my MUX here, gets put into WD, the reg file goes high. But it doesn't save until the next clock edge, right? So the next clock edge is when it saves, which is exactly when it saves. And so that gets put into here, right? You know, looking at the rest of this, right? Like what happens to 8 and 10? Let me see. I can step through this in RARs, right? And I can see what happens, right? So this is the value that goes into register 5, which matches, right? Next time I should get this value into register 8, which is what happens. Right? And then this value gets put into register 10, which is what I get, right? And so forth, right? Down to 12. This is what gets put into 12. This is what gets put into 13, right? On instruction at address 14, right? Hex 14, right? It branches, which should branch back up to 0. So my program counter should change to 0, which is exactly what we see happen, right? We execute at 14, we go back to 0. Right? I could run this again, right? And the same thing would happen, right? None of the registers change because nothing increments, everything's constant, right? That goes up to 14 again, and then goes back to 0 again, right? And continues forever and ever and ever and ever, right? And so this looks good. Questions? So this is what you will be doing in hardware 6, right? And so hardware 6, you essentially have to get 6 instructions to work. But you'll notice, right, with some of what we talked about earlier, probably with hardware 6, you could probably really get everything designed to probably work with more than 6, right? But it's worthwhile to start with testing and seeing if this gets 6 instructions, right? Because you'll make typos, you'll connect things to the wrong port of your MUX, you'll, you know, have a reg file that doesn't have register 0 properly identified or something, right? There's all kinds of little things that'll happen that maybe these 6 don't work, right? And so how do you find out what's broken? Well, we start dragging signals in and start looking at what's supposed to be where, right? Looking at control signals, looking at maybe data that you would see, right? So it goes back to possibly tracing, tracing your architecture to see what's supposed to happen. And then looking at all of those signals in the execute state and see if they match. And if something doesn't match, well, why doesn't it, right? And sort of trace back what happened on where it went wrong. So later in the week, I will look at a bigger program that we'll be using for hardware 7, and I will break my auto. I will put stuff in it that's wrong, and then I will kind of show how we can figure out what's wrong by looking at the sim, which is, after you get your state machines built, or after you get your control unit built, the next 3 weeks we'll be doing that. And so later in the week, I'll take you through essentially what that process will look like. You kind of see it here, but I'll do another example. Cool. Questions? Okay. That is all I